A very good morning, everybody. This is a small lecture on group theory. In order to understand groups, you first need to understand what a set is. So a set is a collection of numbers or items. A set can be a set of numbers, it can be a set of animals, it can be a set of anything. So a set of numbers would look something like this is a set of natural numbers. This is a set of whole numbers. This is a set of rational numbers. A rational number is a set where each element is of the form p by q, where p and q belong to integers, belong to the set of integers. And what is the set of integers? The set of integers would be all the negative and positive natural numbers and 0. So it's going to be -3 dot dot -3 -2 -1 0 1 2, and it goes like that. So what is a function? So let A be two non-empty sets. And F is a selection from A to B. So what is a selection? Say this is a set A and this is a set B. There's an element A in A and there's an element small b in set B. So a function is an operation which transforms A to B. So we would write f of A would be equal to B, and this would hold for elements in A, and it would be mapped to elements in B. So there would be another element, say A1, which would map to B1. Is this the complete definition of a function? No, it's not. Why? Why is this not a complete definition of a function? Because it does not define whether B is unique or not. So what would happen if B is not unique? Suppose FA maps to B and FA also maps to, say, B2. Then the function, is it well defined? It's not, because you have two results for the same function, and that means it is not a function. You have two results for the same operation on A, and that means it is not a function. So one of the key criteria for f to be a function is that B has to be unique. So there you have the definition of a function. Next definition that we come to is what is a binary operation or a binary composition. So let S be a non-empty set. Say it has some elements in it, and S cross S is defined as pairs of elements A and B such that A belongs to S and B also belongs to S. Right? So now if we have a function which maps S cross S to S, then F is a binary operation. So to give you an example, suppose you have the set 1, or you have the set of all natural numbers, and this we name as S. Then we have the ordered pair 1 3. All right, you have the ordered pair 1 3, or you have the ordered pair, say, on a more generic term, we have the ordered pair X Y, where X belongs to S, so S is a natural number, and Y also belongs to S. Now, suppose we define function f of x, y as x plus y. So we have this for an ordered pair, say 1 2, which belongs to S cross S. We have f of x y is 1 plus 2, which is equal to 3, which also belongs to the set of natural numbers. In this case it is S. Thus f is a function from S cross S to S, and hence what we have is the function is basically the operation plus. So plus is a binary operation. So basically an operation which combines two elements of a set to give another element of the same set is called a binary operation. There are various types of binary operations. For example, there's a closure property. It can have, or it may or may not have a closure property. So what is a closure property? Closure property. So say we have this is the binary operation. Let's in short write B hyphen O to symbolize binary operation. Let this be a binary operation. Then for A star B, where A belongs to S and B belongs to S, if A star, oh god, that star looks horrible, but it's a star. If A star B belongs to S, then closure property holds. And we say the set S is closed with respect to the binary operation star. We have another property called the commutative property. So we have the commutative property. What is the commutative property? So we have two elements, A, B belongs to S. We have the operation star A, B, and that will equal B star A. So it's a commutative property. Suppose star is minus, and S is the set of natural numbers. So you take two numbers. We can always verify whether whether minus is a commutative property. Is minus a commutative binary operation? Well, let's check it. Let's find out. So take two numbers in n, say 5 and say 8. So both of them belong to n, and 5 star 8 would be 5 minus 8, which is minus 3, which anyways the closure does not hold. Oh God, what happened there? Closure does not hold, but what we can do is we can we're not checking closure, we're checking commutative. So we take 8 star 5, which would be equal to 8 minus 5 or 3, and that belongs to S. In this case closure holds, but minus is not a binary operation where closure would hold, nor would it be a commutative operation, because clearly minus 3 is not equal to 3. So 8 minus 5 is not equal to 5 minus 8. So it's not commutative. Not commutative. However, if star is a plus, then for the same numbers we can verify 5 plus 3 is 3 plus 5. Hence it's plus is a commutative operation. Similarly, multiplication is a commutative operation. Division again is not a commutative operation. The next property of binary operations would be the associative property. And in case of associative number property, what is an associative operation? So we have three elements, A, B, C, all belongs to S, and this holds A star B. We have this operation star, which is a binary operation, and we have within brackets B star C star of A of that. So A star within bracket B star C, this should be equal to A star B within braces star of C. Again, we can verify for three numbers 1, 2, 3 within of n, and star being minus. We have 1 minus 2 minus 3 is how much? 1 minus of minus 1, which is 2, and 1 minus 2 minus a 3 is minus 4. So clearly minus is not associative. It is not associative. However, plus would be associative because we can clearly see that 1 plus 2 plus 3 is definitely equal to 1 plus within brackets 2 plus 3 equal to 6. So we have two kinds of operations under the binary operation system. One is the associative and one is non-associative. Next, we have the identity property. So what is the identity property? Well, A, B, are two elements of S, and star is the operation. Then A star B would be equal to B star A would be equal to A. Or I would rephrase the definition in a different way. Say identity element, say A is an identity element if for any B belonging to S, and A also belongs to S obviously, then A star B is equal to B star A would be equal to B, which means that any element with which there is a binary operation with A would result into the same binary element, would result in the same element of S, irrespective of whether A is on the left or it's on the right. Normally, this element is denoted by E. Daar.